just protons or even neutrons or some other type of atom that's coming from extragalactic sources at high energies hitting the Earth. So I'm so stoned right now. I think I'm going to hit the waves, dude. Like, yeah. Yes, please enjoy our physics chat, Mad Hatter. I think this will be good. High energy. So since we're going to be talking about ultra high energy physics today, I think you're in the right place, Mad Hatter. So I started to talk about particle astrophysics earlier. I will give you a little bit of an introduction where I repeat what I kind of said earlier, and then we will go into the exact experiment. Is it possible to visibly see light traveling? Like with super slow motion cameras, is it too fast? So when we see something, that is the light that is being emitted or reflected back from that object. So perhaps I'm not following exactly what you mean, but yeah. Yeah, I'm not sure. Let me talk about this introduction, and I'll keep thinking about your question. Yes. Okay. Perfect. So, exciting astrophysics. So I'm reading from my thesis now called Studies in Particle Astrophysics. Exciting astrophysics, according to me, happen far, far away. We live in a boring part of the universe. This allows life and the life sciences to thrive here. However, everything that is interesting in astrophysics takes place far, far away. For example, most gamma ray bursts take place about 1 gigaparsec away from us, which is over 3 billion light years away. So speaking of the speed of, or the question about light, it would take light 3 billion years to reach us from gamma ray bursts. Why are gamma ray bursts interesting? Well, in short, they are nature's most powerful accelerators, and they outshine an entire galaxy when they occur, with luminosity of around 10 to the 52 erg per second. It's a unit we use in astronomy. What is more, the physics behind these exotic events continue to remain mysterious for over 50 years. So we actually looked at the gamma ray burst chapter of my thesis recently. So you might have already caught that live already, but I'm just giving you a little bit of a recap. I'm not going to talk about this full chapter, so if you've heard it already, I'll keep it short. Traditional astrophysical messengers are not able to completely probe physics that take place at the farthest distances and at the highest energies. Since the beginning of astronomy, we have relied on optical light to study objects in the sky. In the last few decades, we have started utilizing light of other wavelengths, such as X-rays and gamma rays. However, light of energy 1 MeV and above can undergo pair production. It's a thing. Light of energy 13.6 EV gets absorbed by hydrogen atoms, the most abundant element in the universe. By the way, this is going to be a quiz question later on. I've asked this before, and I'm going to ask you again later tonight. What is the most abundant element of the universe? It's hydrogen, guys. Light is the astronomer's best friend, but there is an inevitable need for complementary messengers. So I'm like building up the case for other particles as messengers of astronomy. What? Fortunately, in the last century, we have opened up multiple new windows to peer into the universe. About 100 years ago, cosmic rays were discovered by Victor Hess in a balloon-based experiment. In the last several years, the Ice Cube Neutrino Observatory has discovered the first astrophysical neutrinos up to energies of a few PeV